Hello students, all of you are welcome in my YouTube channel neb12 Guru. Hope all of you are fine and you are watching my YouTube channel which is dedicated for chemistry, and I'm bringing you the videos related to 11, 12, BSc first year, second year, third year, fourth year and master's level. So this channel is especially dedicated for chemistry for the students. In today's video, I'm going to describe about the chemical kinetics chapter of BSc first year, and I have already brought many videos related to chemical kinetics. I think you have already watched the videos related to pseudo order reaction, zero order reaction, and first order reaction. First order reaction should not be learned in. It's not necessary to learn in BSc first year, but it is already learned in 12th class. So second order reaction I have already described. In today's video, I'm going to describe about the effect of temperature on rate of reaction. So what is the effect of temperature on rate of reaction? You have already learned about collision theory of reaction theoretically, that when temperature is increased, then energy of molecules will be increased, and when energy of molecules are will be increased, then surely the number of collisions will increase, that will cross the energy of activation, the energy barrier, and will give the product. So rate of reaction definitely increases when temperature is increased. You have learned theoretically in collision theory of rate of reaction, but today I'm going to describe quantitative relationship which shows the effect of temperature on rate of reaction. So the effect of temperature on rate of reaction is studied by Arrhenius, and it is given by the Arrhenius equation. So I'm going to describe here about Arrhenius equation. First of all, I mentioned the Arrhenius equation here. So mathematically, the relation between temperature and rate of reaction is given by Arrhenius equation. So what is Arrhenius equation? Arrhenius equation is given as K equals to A e power minus EA upon RT. This is the Arrhenius equation, where you know K is rate constant, and A is collision factor. What we say collision factor, pre-exponents factor also we call it as. And EA, do you know EA? EA is energy of activation. Similarly, T is temperature in Kelvin, and R is equals to universal gas constant. This is a constant value for gas. So students, Arrhenius equation is given as K equals to A multiplied by E power minus EA by RT. This is Arrhenius equation. So this Arrhenius equation definitely gives the relationship between temperature and rate constant. K represent the rate, more the K value, the more will be rate of reaction. And here this expression definitely relate the relationship between rate constant or rate of reaction and temperature. So in today's class, let us prove the Arrhenius equation mathematically. So this equation we want to prove here. Okay, let us prove this Arrhenius equation mathematically here. Okay. To prove Arrhenius equation, first of all, we have to consider a reaction. Proof. Let us go to proof, and for proof, let us consider a reversible reaction. We can let our reversible reaction for this. Whatever reaction you can let, but I can just write A plus B will give C plus D, and C plus D will give A plus B, and that is in equilibrium. So this is a reversible reaction in equilibrium. For example, if this kind of reaction we have taken reversible reaction in equilibrium, then we can easily write by applying the law of mass action. By applying the law of mass action, when we apply the law of mass action, then at that time we can easily write KEQ, equilibrium constant, that will be equals to, concentration of C multiplied by concentration of D divided by concentration of A multiplied by concentration of B. This is equilibrium constant. I hope that you know the law of mass action. The law of mass action relates the equilibrium constant with concentration of reactant and product. So this is the equilibrium constant KEQ, which is equals to this we can represent like this way. So this is law of mass action, and from Van 't Hoff equation, from Van 't Hoff equation, from Van 't Hoff equation of thermodynamics. So if you just see the Van 't Hoff equation of thermodynamics, then that can be written as like this way: d upon dt ln KEQ is equals to delta E upon RT square. Okay, this is Van 't Hoff equation from the thermodynamics. So this equation you must know to prove Arrhenius equation. For any reversible reaction, we can just write the Van 't Hoff equation for thermodynamics from the thermodynamics. So from the thermodynamics, d by dt, d upon dt ln equilibrium constant will be equals to delta E upon RT square, where the symbols have got their usual meaning. So what are the symbols of these all terms? KEQ is equilibrium constant, you already know it, T is temperature, and delta E is equals to energy of reaction, that we can write E1 minus E2, and R is already universal gas constant and T is temperature. So this is Van 't Hoff equation. So let us know the Van 't Hoff equation of thermodynamics to prove the Arrhenius equation. Then you can simplify this Van 't Hoff equation to prove Arrhenius equation. So let us see here. Okay, let's continue it. Now we can just derive some more ideas from here. D upon dt, this ln KEQ is Q1 upon Q2. This is for forward and this is for backward. It constant for forward and backward. Ln equals to Q1 upon Q2, that you can easily write, that is equals to delta E. Delta E can be easily written as E1 minus E2, I have already told you, divided by RT square, that you can write. So this is just simplification of the given Van 't Hoff equation. Now let us simplify this equation further. So you can write d upon dt. This ln A upon B can be written as ln K1 minus ln K2. Ln A upon B will be equals to ln A minus ln B. This is the formula. So that will be equals to, this you can separate. E1 by RT square you can write, and minus E2 by RT square. This can be separated. This equation can be just separated. So what can you write from here? See, d upon this you can separate, d by dt of ln K1 minus d by dt of ln K2 equals to E1 by RT square minus E2 by RT square. This you can write. Okay, this is the equation, simplified equation. So up to this you can get up to this equation. Okay, d by dt ln K1 minus d by dt of ln K2 equals to E1 by RT square minus E2 by RT square. I think up to here there is no any problem. Okay, just it is simplification. Okay, this, let us say this as equation 1. Let us say this is equation 1. Now we simplify we just simplify this equation into more terms. Equation 1 can be now splitted. As this equation can be splitted as like this way: d upon dt ln K1 equals to E1 upon RT square, that you can write. This is, let's say, equation number 2. Next equation will be d by dt ln k2 equals to E2 divided by RT square. This is, let us say, equation number 3, that you can separate easily because K1 and K2 are different terms, that is for forward and backward. So these two equations you can write, and here you can write integration constant. Sorry, not integration constant, but one of the constant. I is constant here. I is constant. I is constant, and that is independent of temperature. Constant which is independent of temperature. Independent of temperature. This I can be written as a constant which is independent of temperature. So in this way we can get a separate equation for K1 and K2. Students, up to this much you can get it. I have already separated the Bantop equation after simplification. So I will be 0. I will be 0 because that is temperature independent terms. I will be 0. So if you just leave it I, then you can easily write the equation number 2 as d upon dt ln k1 equals to E1 upon RT square, that you can write. And similarly, equation third can be written as d upon dt ln k2 equals to E2 upon RT square. This you can write. Okay, these two equations you can easily get it. So students, you can easily get two equations here after just getting I equals to 0, because that is independent term, a constant term which is independent to temperature. Now we can write in general form. Okay, these two are the equations we have obtained for K1 and K2. Now seeing that two equations, we can generalize the equation. So in general form, you can write now d upon dt ln k equals to this E1 or E2. You can write energy of activation EA divided by RT square. So this kind of equation you can get it. See from here, d upon dt ln k equals to E1 upon RT square is one of the equation, and d upon dt ln k2 equals to E2 upon RT square. In this way, you can generalize the equation as d upon dt ln k equals to E upon RT square for each and every reaction. Okay, so EA is what? Energy of activation. I think you know the energy of activation. This is the minimum amount of energy that you must add in the reaction so that it cross the energy barrier and you get product. So energy of activation, EA is energy of activation, and other terms are already defined. This T is temperature, and R is universal gas constant, and K is rate constant. So this is the general form. Okay, this let us say number 4, and equation 4 equation is Arrhenius equation. So this is one of the form of Arrhenius equation. Okay, d upon dt ln k equals to E upon RT square. In this way, you can get one of the form of Arrhenius equation. Now we can simplify this Arrhenius equation further. You can rearrange this. By just this equation number 4 can be rearranged. As equation 4 can be further rearranged as d ln k equals to this dt can be written in this side EA upon R, this RT, 1 upon RT square, 1 upon T square dt, that you can just rearrange it. This dt we have put on this side. So d ln k equals to E upon R, 1 upon T square dt. That you can easily write like this way. Then integrating both sides. Now let's integrate. Integrating both sides. If you integrate on both sides, integration of d ln k equals to this EA upon R, integration of 1 upon T square dt, that you can integrate on both sides. E and R are constant. Energy of activation is constant for a given reaction, so these two are constant, and T is the variable, so and K is variable, so we can integrate this K and dt. If we integrate this equation in this way, we can easily get it like this way. So what is the integration value of this one? So after integrating, you can get ln k equals to EA upon R, and that is 1 upon t square. Integration is 1 upon t minus 1 upon t plus this ln A is our integration constant. This is integration constant we have introduced here, ln E. If we rearrange this, then we can get it ln K minus ln A equals to EA upon RT minus EA upon RT. So just let us rearrange this. Ln K upon A, this is ln K upon A equals to minus EA upon RT. Now we can simplify this way. Okay, you can write K upon A. This ln can be written in this side, anti-log E power EA upon RT, that you can write, because ln on next side, if it goes then exponential you can write. So K upon A will be equals to exponential minus EA upon RT. Therefore K equals to E power minus EA upon RT. Okay, this is the Arrhenius equation that you want to prove. So see here, what is the Arrhenius equation? This is Arrhenius equation. Okay, Arrhenius equation that you have proved. In this way you can prove the Arrhenius equation very easily. So you can start from Bantoff equation and you can just get it Arrhenius equation, K equals to A multiplied by E power minus EA by RT. In this way you prove it. Okay, now after proving this Arrhenius equation, we can just see what is the significance of Arrhenius equation. Then you can just mention some significance here. So what is A? A represents, A is called pre-exponential factor. Pre-exponential factor, and it is also called collision factor. Collision factor. A is collision factor, or this is collision factor or pre-exponential factor. And EA upon RT. EA upon RT is negative. EA upon RT is negative, and that is exponential factor is negative. Exponential factor is negative. When exponential factor is negative, that represents when t increases, then k also increases. So when we increase temperature, then rate constant increases. If it is not negative, it's positive, then k and t are inverse, but there is negative value, so we can easily write when t increases, then rate constant increases. So when temperature is increased, then rate of reaction increases. Rate of reaction increases. So friends, from Arrhenius equation we can easily prove that for a reaction, when temperature is increased, rate of reaction is increased. Similarly, E power minus EA upon RT is also called Boltzmann factor. Boltzmann's factor, and this Boltzmann factor is the fraction of molecules. This is fraction of molecules that cross EA and change into product. So this Arrhenius equation has got much more significance. Okay, E upon RT is negative, so you can easily relate the rate constant K and temperature. When temperature is increased, then rate constant K is also increased, because T and K are directly related. Similarly, the Boltzmann factor E power minus E by RT is called Boltzmann factor, and that represents the fraction of molecules that change into product after getting the enough energy of activation, or energy barrier. So you can easily get how much fraction of molecules are changed into product. So in this way, Arrhenius equation is a very useful equation that relates rate of reaction and temperature, relationship between rate of reaction and temperature. So friends, if you are reading class 12 chemical kinetics or BSc first year chemical kinetics, then this may be one of the important topic, that what is the relationship between temperature and rate constant that is given by the Arrhenius equation. So you can easily prove it and you can get the significance of it. Okay, in next video, I'll be describing about the how do you calculate energy of activation experimentally from the Arrhenius equation and the numericals related to it. Up to that time, let's say goodbye.